Hello everyone, myself Avnish Tiwari, Assistant Professor in Civil Engineering Department at Sri Ram Swaroop Memorial College of Engineering and Management, Lucknow. Today in this module we are going to discuss about transmission of water. Following topics will be discussed in this module. First one is various types of conduits, basically what is conduits and what are different types of conduit, and next one is hydraulic design of conduit, what is rising main and what will be the economical size of rising main. So, starting with our first point, that is conduits. So, basically conduits are nothing but it is a pipe. In a city, a water supply scheme consists of following parts: water collection from the source, water transportation from source to water treatment plant, and water distribution from treatment plant to city. Basically we can say that conduits is used for transportation of water in two stages. First stage include water transmission from source to treatment unit, and after treating the water, further the water will be transported from treatment unit to the distribution system. So, in two parts we will discuss the transmission of water by the conduits. Next is what are various types of conduits. Basically on the basis of conditions and characteristics of flow, the conduits are grouped into two categories. First one is a gravity conduit and next one is a pressure conduits. So, as mentioned that the classification is based on conditions and characteristics of flow. So, what happen in gravity conduits? In gravity conduits, the water will flow under the action of gravity. Here the flow of water is under the action of gravity. We does not need any extra utility to add pressure for the transmission of water. What will happen in gravity conduits? In gravity conduits, as we all know, there are two lines. First is hydraulic gradient line and next one is a hydraulic gradient line, next one is a total energy line. To know these two things, we have to certain ideas regarding Bernoulli's theorem. In Bernoulli's theorem or Bernoulli's equation, there is basically three heads. First one is pressure head, that is P by rho g. Second one is our velocity head, that is V square upon 2 g, and third one is datum head, that is represented by Z, which is constant. So, here in gravity conduits, the water is flowing under the action of gravity. It means here the pressure head will be 0, and by adding pressure head and datum head we will get hydraulic gradient line. So, this particular head is 0, it means by simply representing the datum head we will get our hydraulic gradient line, which can be seen from this figure. Here at section 1 datum head is Z1, at section 2 the datum head is Z2. As pressure head is 0, so by joining this point and this point we will get a line, and that will represent hydraulic gradient line, and this line will coincide with the water level, the water level in that particular conduits. And what we have to add in order to get total energy line? Simply we have to add velocity head, that is V square by 2 g. By adding velocity head in hydraulic gradient line we will get total energy line. It can be seen that there is a loss which is due to various reason. One of the reason is frictional loss, and that reduces the value of velocity head. Hence, the total energy line is deviating from the straight line. So, in order to get total energy line we have to add velocity head, and the velocity head at this point is v square by 2g and this point v square upon 2g. So, this can be represented as mentioned in the figure. Okay. So, next one is our various forms of gravity conduits. The gravity conduits are in the form of canals, flumes, grade aqueducts and grade tunnels. Gravity conduits can be seen in the form of canal, flume, aqueduct and grade tunnels. Next conduit is our pressure conduit. What will happen in this conduit? In this conduits the water will flow under a pressure greater than atmospheric pressure. Here pressure is greater than atmospheric pressure. It means there we can also see pressure head. In previous case pressure head is not present because the value of pressure is 0 as the water is flowing under the action of gravity. So, how can we get hydraulic gradient line? In order to get hydraulic gradient line, piezometer are installed in a pipe and by joining the level of piezometer, by joining the level of water in the piezometer, we get hydraulic gradient lines. And to get total energy line, what we will do, as we are already aware that in hydraulic gradient line datum head and pressure head are considered. To get total energy line, what we will do, simply we will add our velocity head. After adding the velocity head, we will get total energy line. Okay. The pressure conveyance system are mostly in the form of pipes, as pressure conduits are mostly in the form of pipe which can be of different materials and they are generally closed conduits. Pressure conduits are generally closed conduits and two common types of pressure conduits are closed pressure aqueducts and pressure tunnel, but they are not commonly in use. The most common pressure conduit is simply pipe, which one can easily see in a water distribution system as the water is flowing under the pressure greater than atmospheric value. Next is forms of gravity conduit. As I discussed, gravity conduits can exist in a form of canal, flume and aqueduct. Simple the representation or the sketch of canal can be seen from these two figures and we can easily detect the shape of that particular canal. What will be the shape of that particular canal? So, canal are open channels constructed by cutting a high ground and constructing banks on the low ground. There will be two possibilities, whether the ground will be at a height, certain height, then there we have to perform ground cutting, we have to cut that particular ground, and if the ground is at very low level, then we have to fill it, means we have to perform both cutting as well as filling. So, what will be the best? They are generally constructed in a balanced cut and fill, means there should be equal proportions of cutting and filling and that will result in an economical canal. So, and next one is a depending upon nature of ground, available slopes, design velocities and quality of water, required losses of water, it can be either lined or unlined. So, what is the difference between lined and unlined? Basically in lined canal there is a protective coating on the surface of canal. If it is a surface of canal, then it is covered by a protective coating, okay. And what it will do, basically it will reduce the seepage loss, and this particular form of gravity conduits is generally used for the purpose of irrigation, and we can easily see that both the canals are actually diverting the water for the purpose of irrigation. Next one is a flume. These two sketches represents the sketch of flume. So, what is flume? Basically flume are open channels that are supported above the ground. Both the figure shows that basically these are open channel. Here we can clearly see that this particular structure is supported by trestles and they are generally above the ground. These are the supports. So, where they are constructed? They are basically constructed in order to convey water across a valley and minor depressions or over drains and other obstruction. Means this particular form of gravity conduits are used in order to convey water across the valleys and across depressions, or if there is any obstruction in the path. They are made of masonry, RCC, metal, wood and usually of circular or rectangular in cross section. Means flume can be of either circular or rectangular cross section. Next form is aqueduct. What is aqueduct? Aqueducts are closed rectangular or circular horseshoe sections. Basically the sections are rectangular, circular, it may be closed or horseshoe section. They are basically built up of RCC or masonry work. What they do, basically they again transfer the water, they transmit the water. They are covered or closed, but the action of water is under the gravity. So, they will never allowed to run full, means they are never allowed to run full. They are generally designed for half to 3/4 of the full, half or 3/4 of the full size. Coming to the hydraulic efficiency, which section will be the best? From hydraulic point of view, circular section will be the best as it provides maximum hydraulic mean depth. What is hydraulic mean depth? Hydraulic mean depth is nothing, it is a ratio of wetted area to wetted perimeter. Okay? So, it is a ratio of wetted area and wetted perimeter. So, hydraulic mean depth is maximum, it means maximum area per unit width of per unit of wetted perimeter. So, it will be the most efficient section, means circular form of aqueduct will be the most efficient. Coming to next, water conveyance by pipe. So, pipes are circular conduits and they are used for flowing the water. The flow of water may be under the action of gravity or it is under pressure, it means pressure greater than atmospheric pressure, and this is most common type of conduit. Pipe are the most common type of conduits and it also eliminated all other forms of conduits like canal or aqueduct. They can be of different material. Following are certain materials like pipe can be of cast iron, it can be of plastic PVC, it may be of galvanized iron, it can be of concrete or steel pipes. So, in next lecture we will be discussing the pipe material, why for different materials what will be the properties or what will be their advantages and disadvantages of different pipe materials. Coming to next point, that is hydraulics of flow or design of pressure pipe as a gravity conduits. Here we are going to talk about the design of pressure pipe as a gravity conduits. So, here the size and shape of supply pipeline must be determined by considering hydraulic efficiency, structural efficiency and next one be the economic efficiency, means the cost should not be too high, it should be economically efficient. Okay? So, for that reason the hydraulic gradient should be such that it generate velocities. The velocity should be such that there should be no silting or no scouring, means the velocity should be such that there should be no silting or no scouring. And another reason for the velocity, just optimum velocity, or we can say that what should be the optimum velocity. For velocity so small, what will be the result? If velocity is so small, then in order to fulfill a discharge, require amount of discharge, what we will do? Let us take example. If we have to supply that amount of discharge per second. And there are two options. First one is we can take velocity very low or we can take velocity very high. What will be the cases? We all know that Q equals to area into velocity. When velocity is too low, it means what will happen? Area will be too high in order to fulfill that discharge. So, area increases. If area increases, it means diameter of pipe increases, and if diameter increases, if the dia of pipe is too large, then it will result in higher project cost. It will increases the cost of project. What will happen if we are going to take so larger diameter of pipe? What will happen? Basically, it will increases the loss of pressure head. If velocity is too high, it will increases the pressure head. For this, let us consider a formula, that is FL V square upon 2 GD. This is basically formula for calculating head loss due to friction. What will happen if we are taking velocity too high? What is going to do? Frictional loss will increase. Okay. So, we have to take a optimum value that should be corresponding to non-silting and non-scouring case, and for that purpose the velocity should be kept between 0.9 meter per second to 1.5 meter per second, or this can be raised up to 3 meter per second to 6 meter per second for the point of economy consideration. Okay. So, the pipe should be designed in such a way that available pressure head between the source and city should be capable of fulfilling the demand, as certain head will be lost because of friction. Okay. So, while designing the conduits, following factors should be considered. First one is resistance to flow, available pressure head, allowable velocity of the flow. Okay. And for that particular designing, following formula should be referred. First one is a Hazen-Williams formula for pressure conduits and Manning's formula for gravity conduits. When we are going to design a pressure conduit, we will prefer Hazen-Williams formula, and for design of gravity conduit we will prefer Manning's formula. Okay. Next one is, what is Hazen-Williams formula? As discussed earlier, that Hazen-Williams formula is used for pipe flow. So, how can we design a pipe using Hazen-Williams formula? Here, according to Hazen-Williams formula, velocity equals to 0.85 times of Hazen-Williams coefficient, that is Ch, multiplied by what is R? R is hydraulic mean depth power 0.63 into slope power 0.54, where V is velocity through the pipe, Ch is a Hazen-Williams coefficient, R is hydraulic radius or hydraulic mean depth, and S is slope. So, how can we get the value of that particular constant? Means how can one get the value of Hazen-Williams coefficient? According to CPHEO manual, on the basis of pipe material, the value of Hazen-Williams coefficient can vary, and one can easily conclude that how this coefficient varies on the basis of pipe material. So, for cast iron, ductile iron, mild steel, the values are so on 130, 140. For galvanized iron, if diameter is greater than 50 mm, the recommended value of Ch is 120. But when we are going for design purpose, the value considered is 100, 100, 100, 55 for galvanized iron less than or equals to 50 mm diameter. Okay, so different materials have different values of CH, and the particular selection of value depend upon the material by which we are going to design a pipe. Okay. Next is Manning formula, which is considered for designing a gravity conduits, but it is also applicable for turbulent flow in a pressure conduits. Means this formula can also be used for designing a pressure conduits, but the flow type is of turbulent flow. According to Manning formula, what should be the velocity? Velocity equals to 1 by n r to the power 2 by 3 s to the power 1 by 2. Here r, s, v has usual meanings, that v is velocity, r is hydraulic mean depth, and s is slope, and what is n? N is Manning roughness coefficient, and again this particular value is dependent upon the pipe material. Okay. So these are the conditions, and how according to different conditions the value of n is going to varies. So as per required situation we are going to take the values of n, but if the value of n is not unknown, then what we are going to do? The value of n may be taken as 0.015 for unlined metallic pipes. If the pipe are unlined metallics, then we are going to take n as 0.015 and 0.011 for plastic or other smooth pipes. Okay. So n will be 0.011. Next formula is Darcy-Weisbach formula. This formula is actually used for calculating the head loss, which is equals to F L V square upon 2 G D, where F dash is what? F dash is frictional factor, and this frictional factor is equals to 4 times of coefficient of friction. G is acceleration due to gravity, D is diameter of pipe, L is length of pipe, V is velocity, and HL is head loss. The value of coefficient of friction varies in between 0.02 for new pipe to 0.075 for the old pipes, and if pipe material is given, then for different diameters the values of friction factor are taken as such below, while for designing purpose the value of friction factor can be taken according to the given table, and the same content can be find from CPHEEO manual. Next one is modified Hazen-Williams formula. As in case of Hazen-Williams formula, certain assumptions are made or certain considerations are taken while deriving the formula. So first limitation is that Hazen-Williams have taken CH as a dimensionless, but actually that particular term is not dimensionless. It is having a dimension of L to the power minus 0.37 to the T to the power minus 1. Next one is, while considering the value of CH, they just consider limited things. In case of Darcy-Weisbach formula, the formula is dimensionally consistent. In case of Hazen-Williams coefficient CH, considered independent of pipe diameter, velocity of flow, and viscosity. However, to be dimensionally considered to be representative of friction conduits, it must be dependent upon relative roughness of the pipe and Reynolds number. And when these two terms, means when we have considered friction factor and the value of CH, there is an error, and the error estimated is about plus minus 45%. And next limitation is that the constant 0.85 was derived by taking the value of hydraulic mean depth is 0.3 meter and the slope of line, or we can say that frictional slope is about 1 in 1000. But while deriving the design or while designing the pipe, we are not going to take R as this and slope as this value. We are going to design it, we are going to use it for different values. Okay. Next one is, what is rising main? Basically rising main is a pipe through which pumped water is transported to next unit. Okay. Pump water is transported to next unit. Generally rising main should convey the water direct from pump to the high level of storage tank without being tapped or having water drawn off in any way. For a prefixed demand, water may be pumped through a bigger diameter of pipe at a low velocity or through a lesser diameter of pipe at a high velocity. The larger diameter of pipes are costlier, which will increases the cost of project, and smaller diameter pipes are relatively cheaper but requires higher velocity, which results in higher head loss. Thus we have to go for more power for pumping. So pipe should be designed for economic value, and what will be the economical diameter, and that economical diameter for rising main will be d equals to 0.97 to 1.22 under root q, and the velocity preferred for designing is 1 to 1.5 meter per second for getting the economic diameter of rising main. And while considering the economic dia of rising main, the cost, operation, maintenance and construction should be optimum. Okay. That's all are the references. Thank you.